When you look up at the night sky, you are only seeing a tiny fraction of what is actually there. Everything visible to the human eye, every star, planet, and swirling nebula, accounts for just 5% of the universe. The rest is hidden. About 27% of the cosmos is composed of dark matter, an invisible substance that acts as the fundamental glue holding galaxies together. We know it exists because of a persistent gravitational discrepancy. In the 1970s, astronomer Vera Rubin measured the rotation of spiral galaxies and found that stars at the outer edges were moving at the same high speeds as stars near the center. Think of a playground merry-go-round. If it spins at a violent high speed, any child holding onto the bars will be flung into the dirt, unless a powerful harness holds them in place. Galaxies are spinning so fast that the gravity from their visible stars is nowhere near strong enough to keep them intact. These galaxies should have scattered into the void long ago. The only mathematical explanation for why they remain together is that they are engulfed in a massive, invisible halo of dark matter, providing an immense amount of extra gravity. This leaves us with a choice. Either dark matter is a physical reality we simply haven't caught yet, or our current understanding of how gravity works is fundamentally flawed. To test these theories, astronomers look for gravitational lensing, a phenomenon where massive objects warp the fabric of space-time. It is similar to looking at a distant light through the thick glass base of a wine goblet. The glass stretches and magnifies it, creating a distorted image of what lies behind it. When we observe distant galaxies, their light is bent by the mass of galaxy clusters in the foreground. However, the visible stars and gas in those clusters don't have enough mass to create the level of distortion we see. There is a massive amount of invisible material doing the heavy lifting. The most direct proof of this material comes from the Bullet Cluster, the aftermath of two galaxy clusters colliding at millions of miles per hour. During the crash, the normal matter, mostly vast clouds of hot gas, slammed together, experienced immense friction, and stalled in the center of the collision site. But when scientists mapped the gravity of the cluster, they found it wasn't where the gas was. The bulk of the mass had passed right through the crash site without slowing down. Because the gravity physically separated from the visible matter, dark matter cannot be a math error. It must be a tangible, physical substance that doesn't feel the friction of a collision. This substance is not made of normal atoms. It doesn't absorb light, so it isn't clouds of dark gas, and decades of surveys have proven there aren't enough black holes to account for the missing mass. Instead, physicists believe dark matter consists of undiscovered subatomic particles forged in the high-energy environment of the Big Bang. Most models focus on cold dark matter. In this context, cold means the particles move slowly. This lack of speed is crucial, as it allows them to clump together under their own gravity to form the seeds of galaxies. The two lead suspects are WIMPs, heavy particles that interact only through gravity and the weak nuclear force, and axions, which are incredibly light and behave more like a wave permeating the galaxy. Since these particles are invisible to traditional telescopes, scientists have to go to extreme lengths to catch a single one. To detect these particles, we go deep. Experiments are buried miles underground in abandoned mines and beneath mountains to shield them from the constant rain of cosmic radiation at the surface. In this subterranean silence, massive detectors like Lux-Zeppelin and Xenon-NT wait. They use tons of ultra-pure liquid xenon to set a trap. If a single dark matter particle strikes a liquid xenon nucleus, it should release a microscopic flash of light. For decades, detectors have been getting larger and more sensitive to catch this signal. However, in 2025, these experiments hit a physical limit known as the neutrino fog. Solar neutrinos are so abundant that they are now bouncing off the xenon atoms, perfectly mimicking the signal we expect from dark matter. Navigating this background noise is now the primary challenge for underground labs. While the search continues underground, our newest space telescopes are finding evidence of dark matter's influence in the very first stars. In 2026, data from the James Webb Space Telescope supported the existence of supermassive dark stars. These theoretical objects are fueled by the heat of annihilating dark matter, rather than the nuclear fusion seen in stars like our Sun. These dark stars could grow to 1 million times the mass of the Sun. Their existence would explain how supermassive black holes formed so quickly in the early universe, providing a new link between the particle we are hunting and the structure of the cosmos. To see the full impact of this substance, we have to go back to the aftermath of the Big Bang, when the universe was a hot, chaotic plasma. Because dark matter was cold and slow, it began clumping together much earlier than normal matter could. These invisible clumps created gravitational valleys. As the universe cooled, hydrogen gas pooled into the deepest intersections, igniting the first stars. Over billions of years, this formed the cosmic web, a sprawling network of dark filaments with galaxies decorating its densest points. Without this invisible scaffolding, gas would have remained diffuse. The stars, the heavy elements, and the planets required for life would never have formed. Dark matter is physically present in the room with you right now. As the Earth moves through the Milky Way's halo, roughly 10 billion particles pass through your body every single second, without a single interaction. We are finally building the tools to see this hidden structure. The Rubin Observatory is currently conducting a 10-year survey to map the cosmic web across the southern sky in high definition. Simultaneously, the Nancy Grace Roman Space Telescope will soon begin surveying hundreds of millions of galaxies, measuring the interplay between dark matter and dark energy across billions of years of history. For nearly a century, dark matter has been the invisible architect of our reality. We are finally entering an era where we can see the scaffolding that holds the universe together.